All right, so imagine this. Like, you're the philosopher king, right? And you're looking for, like, the very foundation of all thought, like principles that are so basic they apply to, well, everything.
Oh, absolutely. Yeah. Like, where do you even start with that kind of inquiry, right?
Exactly. It's a head scratcher for sure. And it kind of leads us to what we're diving into today, these things called logical constants, which honestly are a lot trickier than they sound.
Yeah, you'd think constant, like it's got to be straightforward, right? But it turns out even figuring out what counts as one of these logical constants is, well, a bit of a philosophical puzzle in itself.
It's kind of funny, like the smartest people have been debating this for ages, and that's kind of what makes it so fascinating to like dig into.
Totally. Like the stuff we're looking at today, it goes deep right to the bedrock of logic itself. And each text we've got here, they're all trying to pinpoint these, well, these core elements of reason. So we've, looked at them all, trying to pull out the most interesting ideas for this deep dive.
And as always, our mission is to take these crazy philosophical ideas and, well, make them make sense. So by the end of this, hopefully we'll all have a better grasp of like how people have tried to define these logical constants, basically, how to analyze like the very structure of how we think, right?
Exactly. It's like getting a peek under the hood of thought itself.
Okay, so to start, how about we like rewind a bit, go way back to one of the first ways people thought about this?
Yeah, so back in the day, before a guy named Frege kind of shook everything up, the main idea was that these logical constants were basically what they called syncatogrammatic terms. Now, this was all part of what they called term logic, where they thought every statement was built from a subject and a predicate, linked together with some special words.
Okay, so it's like on one side you have these catagrammatic words, the nouns and adjectives, the stuff we talk about like Socrates or runs, or huge words with meaning on their own, right?
Right, those are the building blocks. Then you have these syncatogrammatic words like only, every, necessarily, or. These don't really mean anything by themselves, but they like give structure to those catagrammatic terms, help them make a complete thought.
It's like, I don't know, the difference between the bricks of a building and the mortar that holds them together, right?
Yeah, a perfect analogy.
Hmm.
These syncatogrammatic words, they were seen as providing the form of this statement, while the catagrammatic ones gave you the matter. Like this 14th century logician, Buridan, he said it pretty clearly. Categorical terms, they're the matter, while syncatogrammatic terms, they're about connecting, negating, specifying quantity, all that stuff. That's the form.
Okay, got it. So everything nice and neat, then along comes Frege, and things get a little messy.
Yeah, he kind of threw a wrench in the works. Frege, with his idea of function argument for propositions, well, it totally changed how we understood logical form. Instead of that subject-predicate thing, he showed us that sentences could be seen as like applying functions to arguments.
Like, what does that even mean? Could you give an example?
Sure, let's take that Moby Dick sentence again. Every boat is smaller than Moby Dick.
So, in the old system, boat would be the subject, and things smaller than Moby Dick would be the predicate.
Right. But Frege comes along and he's like, nope, not so fast. He'd analyze it more like, for all x, if x is a boat, then x is smaller than Moby Dick. He saw this as a second-level function. For all x, if something x has property f, then it has property g. And that's applied to two first-level functions, which are being a boat and being smaller than Moby Dick. I know it sounds a bit complicated.
No, no, keep going. This is like the good stuff.
Okay, so here's the thing. This is where it gets really tricky for our logical constants. See, if every functional expression is syncatogrammatic just because it needs arguments, then, well, even normal predicates like is smaller than would get lumped in with the logical stuff, and that totally blurs the lines we're trying to draw.
Yeah, that makes sense. It's like suddenly everything's syncatogrammatic, and then what's the point of the distinction, right?
Exactly. So that neat little division between catagorematic and syncatogrammatic, which worked so well in the old system, just didn't fit with Frege's new way of looking at things. It became this big question. Do we call all functions syncatogrammatic or just some special kinds? Neither answer really worked to pin down what we intuitively think of as the truly logical stuff.
So Frege kind of showed us that this simple idea of logical constants being the grammar glue wasn't going to cut it.
Yeah, it wasn't that simple, but even though that direct connection got weaker, this idea that they're crucial for structure, it's stuck around. You can see it popping up in, like, Wittgenstein, who compared them to punctuation marks, and Russell, who thought they showed logical form instead of being, like, actual parts of the proposition. And then later you have folks like Quine and Dummett, who pushed this idea of logical constants being the grammar particles of a language.
Okay, so let's talk about this whole logic as grammar thing, because that seems like, I don't know, a natural step from what we just talked about.
It is, absolutely. So Quine and Dummett, they came along and said, hey, maybe these logical constants are exactly these grammar particles, like the basic building blocks we use to make bigger sentences from simpler ones, and everything else, the non-logical stuff, that would be the basic parts of those simple sentences, the words for things and their properties.
Okay, and when you look at like standard first order logic, that kind of seems to fit, right? Like and or not. And those quantifiers like every and some, those are the logical operators. And then you have individual names and predicates, which are the non-logical part.
Exactly. In first-order logic, which a lot of people use as like a starting point, all those terms and predicates like cat or is blue are prime examples of non-logical constants, while the operators and connectives, they're the logical ones.
Hmm.
But, and here's the thing, this might be a bit misleading, because first-order logic was kind of built with a grammatical structure that, well, reflects what we think of as logical.
It's like we made it that way on purpose.
Yeah, exactly. So it's pretty easy to cook up, like, artificial languages where this whole grammar thing falls apart. Like, imagine we invent a new word. Let's call it cat exists, and it means there's at least one cat such that. Now, grammatically, it could act just like our normal quantifiers, right? Like there exists.
So grammatically, it would be a logical constant, according to Quine and Dummett, but
But it's clearly talking about cats specifically, right? Which is not what we'd expect from a truly universal logical thing.
yeah, that cat exists thing is a great example. It shows that just being a grammar particle, well, it ain't enough to make something logical. The content of what it means, that matters too.
Absolutely. And get this, you could even flip things around. You could mess with the grammar of first-order logic so that the usual connectives like and or, they aren't the basic particles anymore. They could just be part of some bigger category handled by a more general grammar rule.
So basically, just looking at grammar, it's too flexible. You could create all sorts of languages where the logical constants are totally different, just based on how you set up the grammar.
And unless we have some other way to pick out which languages and which grammar descriptions are the right ones, well, using grammar alone to define logical constants, it just doesn't seem strong enough to capture what we really mean.
Now, Quine himself, he had a more, I guess, sophisticated reason for focusing on grammar, right? It wasn't just about any random language.
Oh, right, yeah. Quine, he was all about using the language and grammar that work best for science, for expressing our theories clearly. He thought the grammar should, like, perfectly reflect the truth conditions of our sentences. So this whole thing about inferences preserving truth based on grammar, it wasn't about some magic in the particles themselves, but about picking a language where grammar is a good guide to what's actually true.
So it's less about what is a grammar particle and more about what should be in our ideal language for science.
Exactly. And this idea, it even applies to, regular languages like English. Linguists, they have all these fancy grammar structures, sometimes they call it logical form or LF, to figure out what sentences really mean, especially when they're ambiguous. And we can try to use these structures to find our logical constants, maybe by looking at certain types of words like conjunctions, prepositions, or those functional words like tense markers and pronouns. They often contrast these with like substantive words like nouns and verbs.
But then you gotta wonder if there is this connection between how our language works and these traditional logical constants. Why does that even matter for this whole philosophical question? Why should we treat inferences based on like functional words any differently from those based on substantive words?
That's the million-dollar question, and maybe linguistics and cognitive science will give us some answers eventually. For now, it's an open question, whether this overlap means something deep or is just, a coincidence. But it definitely tells us we can't just say grammar function equals logical status.
Right, right. So grammar alone doesn't seem to give us the answer our philosopher king is looking for. Let's move on. How about this meaning as truth conditions thing, which is often connected to a guy named Davidson?
Ah, yes. So Davidson, he was a student of Quayle, and his approach, it kind of shifts the focus away from structure in grammar and toward the role of words in like a theory of meaning. Specifically, he said, logical constants are those expressions that have a special role in a Tarskian truth theory for a language. Now, Bear with me for a second. I know this sounds technical.
Yeah, maybe just a quick reminder of what a Tarskian truth theory is for those who don't have a PhD in philosophy. Haha.
Of course, of course. So a Tarskian truth theory is basically a way to define what truth means for a sentence in a language. You do it by breaking down sentences into simpler parts and saying when those parts, and eventually the whole sentence, are true.
Hmm.
It uses base clauses for the most basic sentences and recursive clauses to deal with bigger sentences built from the simple ones.
Okay, so you'd have base clauses for simple sentences, and then these recursive clauses that tell you, like, how the truth of a compound sentence, like one with or some in it, depends on the truth of the smaller parts it's made of.
Exactly. And Davidson's big idea was that logical constants are precisely those things in a language that make you need a recursive clause in this kind of truth theory. Like or and some from our earlier examples, they'd probably require those clauses.
Because they're the things that link those simpler sentences together, right?
Right. The idea is that the way these constants work, you need a rule that can be applied over and over again to figure out the truth conditions of more and more complex sentences.
But again, it seems like the details are super important. Like, Davidson himself knew that what counts as logical form in this view depends on how you set up the truth theory itself, right?
Oh, absolutely. You can build different truth theories for the same language, and while they might all agree on whether a sentence is true or false in the end, they could disagree on which expressions need those special recursive clauses. So whether something's a logical constant could depend on how you choose to analyze the language in your truth theory.
And you mentioned some interesting examples in the source material. One was about those gradable adjectives like large.
Right, right. So you could imagine making a recursive clause for large, maybe something like X is a large Y is true if X is a large satisfier of Y. But to make that work, your meta-language, the language you're using to define truth, it'd have to be more powerful, able to handle this idea of a large satisfier. So the question is, can you rule out that kind of meta-language without already assuming something about whether large is a logical concept?
It's like we're back to trying to define logic by already using logic, kind of a circular thing.
Exactly. And the other example was about truth functional connectives. Instead of having separate recursive clauses for each one, like and, or, and so on, you could maybe deal with them in the base clauses by, like, directly assigning them their truth functional meanings. Then you'd have one general recursive clause for any truth functional connective. But this means your meta theory has to be able to talk about truth functions, which makes it more complex.
So it seems like, just like with grammar, this truth-theoretic approach needs some extra rules to tell us for sure what's a logical constant. The framework itself is too flexible. It lets you analyze things in different ways that could give you different sets of logical expressions.
That's a great summary. And philosophers like Davidson, they probably knew about these problems. Like, remember how Quine had those pragmatic reasons for focusing on certain languages and grammars? Well, Davidson might say that using a simple, well-understood logic in your meta-language is more important than trying to handle stuff like large in those recursive clauses. The debate then becomes, like, which pragmatic reasons are the most important for figuring out what logic really is?
Okay, so we've looked at structure through grammar and meaning through truth conditions. Now, let's tackle something that seems kind of different. Topic neutrality. This is the idea that logic isn't about any particular subject matter. It applies to everything.
Ah, yes, the idea of universal applicability. It's a seductive idea, right? Logic, it's like this tool we can use no matter what we're thinking about, so it makes sense to think that logical constants, they're the words that reflect this topic-neutral nature. They shouldn't be tied to any particular subject.
Like, obviously, words like horse or planet, they have specific topics, but if and not, they seem like they could be used in any context you can imagine.
Exactly. But when you try to actually define this idea of e-topic neutrality, it gets tricky. The source material even calls it the antinomy of topic neutrality because, on the one hand, logic seems totally general, anything can be negated, any two propositions can be linked by and. But on the other hand, logic also seems to be about those specific logical notions like negation, conjunction, and the ideas behind all and some.
It's like a paradox, right? How can something be both about specific concepts and totally general, about nothing in particular?
That's the puzzle.
Oh.
And this logician, George Boulos, he pointed this out, saying we could easily say that logic is about negation, conjunction, identity, all, and some. So this whole idea of being topic neutral is, well, pretty slippery.
Okay, so the source material mentions this guy, Ryle, and his attempt to define topic neutrality using what he called a foreigner criterion. What's that about?
Okay, so Ryle, he basically said that a word or expression is topic neutral If someone who only understood that word, like a foreigner who didn't know the rest of the language, wouldn't have any clue what a paragraph containing that word was about.
So at first glance, words like is and if, they seem to fit that.
Right. But then you realize even those seemingly logical words could give you some hint about the topic. Like because kind of suggests a cause and effect thing. It implies we're talking about a non-person. Tenses have to do with time. And quantifiers like every and a few, they assume we're dealing with separate countable things.
So it's actually super hard to draw a clear line. Like, is topic neutrality an all or nothing thing? Or is it more like a spectrum where some words are more topic neutral than others?
Exactly. Maybe truth functional expressions are more topic neutral than quantifiers, and quantifiers more so than modal operators. But Ryle's criterion doesn't really tell us how to make those distinctions, or even if they make sense.
And it seems like trying to define aboutness more precisely, well, it doesn't really solve the problem either. The source talks about Goodman's idea of absolute aboutness, which ends up being circular, and Lewis's account, which weirdly makes all necessary truths topic neutral.
Right, so Lewis's approach doesn't really help us separate logical truths from other kinds of necessary truths, like math or metaphysics. And if we're trying to use topic neutrality to define logic, well, we can't start by already assuming what logic includes.
Okay, so if aboutness doesn't give us a solid foundation, what else can we do? The source mentions two other ways to think about this idea of logic being not about anything in particular.
Right, so the first one focuses on the idea that, like, topic-specific words are able to discriminate between things in our world. For example, is a horse separates horses from, say, statues. But logical constants, they shouldn't do that. They should treat everything equally. Like expressions like is a thing or is identical with, they don't inherently pick out any specific object.
So this leads to the idea of being insensitive to individuals, where logical expressions don't care about the specific identities of the objects they're talking about.
Exactly. And as we'll see later, this can actually be defined really precisely using math through this concept of permutation and variance.
Interesting. And what about the second way to think about it?
The second one is about universal applicability, which connects to the idea that logic is useful for any topic because it's tied to the very conditions of thought itself.
So even something like arithmetic, which is about numbers, could be considered topic neutral in a broader sense because its principles apply to any kind of rational thinking.
Exactly. Frege was a big believer in this, for example. And this whole thing about defining logical constants through their inferential rules, like how we introduce and eliminate them in arguments, it ties into this idea of universal applicability, right?
Yeah, because the rules should be valid in any context, regardless of the specific content.
Exactly. The idea is that if we can define logical constants through rules that are like fundamental to the very act of thinking, then it makes sense that they would apply universally.
Okay, so maybe we can resolve that antinomy of topic neutrality by distinguishing between these two senses, not being about specific things and being applicable to all reasoning. But then the question is, which one, if either, really defines logic? This brings us to the next section, logic as invariance, and specifically this concept of permutation invariance. This sounds pretty mathematical.
It does get a bit technical, but the core idea is actually pretty elegant. And it directly relates to that first sense of topic neutrality, the insensitivity to individuals thing. Basically, it says that logical constants are those expressions whose meaning, in a very precise mathematical sense, doesn't change no matter how you rearrange the objects you're talking about.
So a permutation is basically just shuffling things around, right? Like if you have a bunch of objects, a permutation is just a way of rearranging them so each one ends up in a different spot, like shuffling a deck of cards.
Precisely. Now, for a predicate to be invariant under a permutation, it means that if you look at all the objects that the predicate applies to, and then you shuffle those objects around according to your permutation, you end up with the same set of objects that the predicate originally applied to.
So like if you take the predicate is a vowel and you apply it to all the letters of the alphabet, you get the set of vowels, right? But if you shuffle all the letters around and then apply the predicate again, you might get a different set because some vowels might have been swapped with consonants. So is a vowel is not invariant under permutation.
Exactly. But if you take a predicate like is a letter in the first half of the alphabet, then no matter how you shuffle the letters, the set of letters that satisfy that predicate will always be the same. So is a letter in the first half is permutation invariant.
Okay, so how do we apply this to like more complex expressions like those quantifiers and connectives?
Well, the general idea is that an expression is permutation invariant if its extension, basically, what it refers to, like the set of things it's true of, doesn't change under any permutation of the objects we're talking about. For stuff like connectives and quantifiers, which have more complicated meanings, the definition gets a bit more technical, but the basic principle is the same. Their meaning shouldn't depend on how we shuffle the objects around.
And it turns out that a lot of our standard logical constants like and, or, not all, some, and even identity, they all fit this permutation invariance thing, right?
They do. Even those fancy quantifiers that talk about like infinite sets, they pass the test too, because the property of being infinite, that doesn't change under shuffling. On the
Yeah.
other hand, stuff like proper names, specific predicates like is red or is a horse, and quantifiers that talk about specific things like some philosophers are exactly two planets. They're generally not permutation invariant.
Because they depend on the particular things they're referring to, right?
Right. And the cool thing is, there's been some really hardcore math proofs that show this connection is pretty strong. Like all the relations you can define in systems like Principia Mathematica, they're all permutation invariant. And the other way around, all permutation invariant operations, you can define them using things we intuitively consider logical.
So that's a pretty good sign that this is a good way to distinguish logical from non-logical stuff.
It is. Tarski even thought this whole thing was like a generalization of Klein's Erlanger program in geometry, where different geometries are defined by what stays the same under different transformations. So logic, in this view, would be about what stays the same under the most general transformations, all permutations of the objects we're talking about.
But like with everything else, there are some limitations to this, right? The source mentions that this mainly applies to extensional operators, which are those that deal with like sets of objects and not so much with the deeper meaning of things. So what about things like modal logic with necessity and possibility, or temporal logic, which is about time? Do those fit in?
That's a good question. People have tried to extend this permutation thing to those logics by considering permutations of like possible worlds or moments in time instead of just objects in a single world. But this gets really strict. Like the necessity operator in a logic called S5, it often counts as logical under this extended definition. But the necessity operator in a weaker logic called S4 usually doesn't, because the specific way those worlds are connected, it's not preserved by all permutations.
And then there's the problem of deciding which structure should be preserved by the permutations, right? Like, why treat the structure of possible worlds differently from the structure of, say, sets?
Exactly. If you start picking and choosing which structures stay fixed, it gets hard to justify why some are special and others aren't, and the whole distinction between logical and non-logical could get blurry again.
Okay, so the source also talks about some specific arguments against this strict permutation invariance thing. One was this thought experiment with a wombat disjunction. That sounds kind of weird.
Oh, it's pretty clever. So this guy, McGee, he imagined a logical connective that acts just like or if there's at least one wombat in the world, and just like and if there are no wombats.
Okay, so how does that challenge permutation invariance?
Well, this connective would technically be permutation invariant because its behavior only depends on whether there are any wombats or not, and that doesn't change when you shuffle things around. But its meaning, it seems to depend on this very specific thing, wombats, which is not what we'd expect from a truly universal logical constant.
Yeah, that's a great point. It shows that maybe focusing only on what a connective applies to its extension misses something important about its meaning. The example with the approximate mass predicate makes a similar point,
Right.
right? Like the idea that something could be considered logical just because of a random fact about the world.
Absolutely. If, by pure chance, all the objects in our world had different masses, then the predicate has approximately the same mass as would act just like identity, which is a super basic logical constant. But it feels wrong to say that whether approximate mass is logical depends on whether there are any objects with the same mass.
And then there were those weird connectives, the hashtag and matent ones, which were defined using necessary truths, like water is H2O and no male widows. Even if those statements are necessarily true, and even if the resulting connectives end up behaving like normal logical ones, they still feel different, like not truly logical, because their meaning is tied to these specific facts about the world, even if those facts are necessary.
Right. It highlights the difference between just looking at the extension of something, like what it applies to, and looking at its meaning, its intention. There was this philosopher, Scher, who tried to deal with this by defining logical terms through their extensions in a specific way. But that just raises a whole bunch of other issues because usually we tell logical connectives apart by their meaning, how we use them in arguments, not just by the truth functions they happen to express.
Okay, so permutation and variance, while it's a powerful tool, it doesn't seem to be the whole story. It tells us something about what these constants refer to, but not about their deeper meaning. So let's move on to logic as inference, and the idea that logical constants are defined by their rules in a system of reasoning.
This is a really cool approach. The basic idea is that logical constants are best defined by the rules that tell us how to use them in arguments, how we can introduce them into a proof, and how we can derive conclusions from them.
So a good example is the rules for and, right? If you know A is true and B is true, you can conclude A and B is true. And if you know A and B is true, you can conclude that A is true and B is true. And the idea is that understanding those rules, that's all you need to fully understand what and means.
Exactly. Anyone who can think logically should be able to understand and use those rules, and in doing so, they've basically grasped the meaning of and. This is super different from that no male widows connective. Even if you made rules for it, understanding those rules would probably require you to already know what male and widow mean, and those are clearly not basic logical concepts.
But of course, when you actually try to write down these rules, it gets pretty complicated, right? Like, what kind of system do you use? Do you allow multiple conclusions? What about those structural rules? And how do you handle quantifiers? All those choices affect which things end up being considered logical.
Absolutely. The way you set up your system matters a lot. And it can even lead to different logics altogether, like intuitionistic logic versus classical logic, which differ precisely in the rules they accept.
And the source mentions two ways to think about what it means for a set of rules to characterize a logical constant: semantic value determination and sense determination. What's the difference?
So semantic value determination, it's the idea that the rules are good enough if they, along with some general assumptions about meaning, can uniquely fix what the constant refers to. Like for connectives, this would be the truth function they express.
But like with permutation and variance, this might not be enough, right? You could have two different constants that mean different things in everyday language, but happen to have the same semantic value and similar rules, like that W quantifier we talked about earlier, which was technically equivalent to there exists, but had a much weirder meaning.
Right, just learning the rules for W wouldn't give you the full understanding of what it means, like learning the rules for exists does. So this suggests that just looking at the semantic value, it might miss something important about the meaning or sense of a constant.
And that brings us to the second interpretation, sense determination, which basically says that the rules should completely determine the meaning of the constant so that anyone who understands the rules automatically understands the meaning without needing any extra knowledge.
Exactly. The idea is that your grasp of the logical constant should come directly from knowing its rules, from recognizing when an inference based on those rules is valid in a, basic fundamental way. This approach could potentially tell apart logical constants that are technically equivalent but have different meanings, like different ways to define or, based on which rules seem most fundamental or primitively compelling.
The source also talks about Pryor's famous Tonk connective, which is a bit of a wrench in this whole thing. Can you remind us what that is and why it's a problem?
Tonk. So Pryor, he basically made up this connective with a specific introduction rule. If you know A is true, then you can infer A tonk B for any B. And the elimination rule. If you know A tonk B is true, you can infer B. Now, the problem is, if you combine these two rules, you can basically prove anything from anything, which makes the whole system meaningless.
So Tonk shows that just having rules isn't enough. The rules themselves have to be well behaved in some way.
Exactly. Tonk doesn't completely destroy this whole approach, but it definitely shows that we need to be careful and have some criteria for what counts as a good set of rules that actually define a meaningful logical constant. People like Belknap and Hacking have suggested different ways to do this.
And there's also Prowitz's idea that any sound introduction rule can define a logical constant, and then the elimination rules are justified based on that. And then there's this concept of harmony between the rules.
Right. Harmony basically means that the elimination rules shouldn't let you infer more from a statement than what the premises used in the introduction rules would have justified. It's about having a kind of balance in how the rules define the meaning.
Okay, so this inferential characterization thing, it gives us a cool way to define logical constants based on how we actually use them in reasoning, which ties back to that universal applicability idea.
Absolutely. It tries to ground the meaning of logical constants in the basic principles of how we think.
All right, so we've looked at a bunch of these like analytical approaches to defining logical constants, focusing on their properties. But now let's shift gears and talk about this logic as tool perspective, which
Oh.
is also called the pragmatic view.
So this view, it kind of gives up on finding some special property that all logical constants share. Instead, it defines them based on what logic is supposed to do. Like if we think logic's main job is to organize scientific theories, then the logical constants are the ones that are essential for that task.
And the source mentions this requirement of minimalism, where you only count as logic the stuff that's absolutely necessary for the job.
Exactly. This can lead to different conclusions about what's logical. Like if you can handle identity just fine using regular predicates and some axioms, then a strict pragmatic view might say identity isn't part of core logic. Same with modal operators. If they're not needed for basic science, they might get excluded too.
So it's not about what these things